In this video, we will be discussing more applications of the normal distribution. But before we do this, we'll introduce a new piece of notation known as a z-score. A z-score is a number z sub alpha which satisfies the following equation. The probability that 0 is less than a standard normal random variable is less than our z-score equals alpha. We can see what this represents on a standard normal bell curve. We're looking for a number on the z-axis of a standard normal random variable such that the area between 0 and that positive z number equals alpha. Let's look at an example of finding a z-score. Suppose we want to find z sub 0.23237. Let's draw a picture of what it is we're looking for. We have a standard normal curve centered at 0. We have our z-score, z sub 0.23237. We want the area between 0 and that z-score to be 0.23237. So that's this area. Here we have a portion of the standard normal CDF table found in the appendix of your textbook. Recall what this table gives us. Graphically, on a standard normal bell curve, this gives us the total area to the left of some non-negative z number. What we're looking for is a number that creates a specific area. But notice we have the area between 0 and that number. So what we need to do is recall that half of a standard normal curve has an area of 0.5. So really, if we were looking at the total area to the left of the z number that we're looking at, we would take 0.5, half the curve, plus the 0.23237 that we already have, for a total area of 0.73237. Now what we do is we look in the interior of our CDF table for this area. And if you look for a little while, you'll notice it's right here. And then we ask ourselves, what z number gives that area? And the answer is 0.62. So our z-score equals 0.62. So again, to reinforce what a z-score means, if z sub 0.23237 equals 0.62, that tells us that the probability that 0 is less than a standard normal random variable is less than 0.62 is equal to 0.23237. Let's look at a question similar to that of finding a z-score. Suppose we want to find the value c so that the probability that negative 0.2 is less than z is less than c is equal to 0.46991. It's a good idea to draw a picture of what it is we're trying to find. The problem is we don't know if c is a negative number or if c is a positive number. So the first thing we could do is we could figure out the total area between negative 0.2 and 0. We know that the area between negative 0.2 and the number c is supposed to equal 0.46991. So if the total area between negative 0.2 and 0 is greater than this value, then c must be a negative number. If the area in green is less than this value, then c must be a positive number. Solving this using the techniques from the previous video, we see that the area is 0.07962. So we know the number c is a positive number. From the problem, we know that we want the total area between negative 0.2 and the number c to be 0.46991. So if we subtract off the 0.07962, then the area in blue, which is the area between 0 and our number c, would be 0.39029. So now we have a question identical to a z-score question. We know the area between 0 and the number we're looking for is 0.39029. So using the exact same technique we used previously to solve for our z-score, we can find the value of c. And if you do this, you'll find the value of c is approximately 1.23. Again, just to remind you how we found this, we know the area from 0 to C is 0.39029. If we add the other half of the curve, the left half of the curve, we are looking for the area 0.89029 in our table. And if we look back at our table, the closest we can find to 0.89029 is right here, which is created by 1.23. So C is 1.23. We can test this by solving the problem P, the probability of negative 0.2 less than Z less than 1.23. And if we solve this problem using either the table or our calculator, we should find that it's approximately equal to 0.46991, the area we were looking for. At this point, you should pause the video and take some time to read the example in your book, which shows a similar type problem but for a non-standard normal. It also shows you how this information can be used in practice. Now let's talk about surveys and confidence intervals. The types of surveys we'll be considering are surveys which have two possible answers. Examples of these surveys are surveys which have an answer of yes or no, agree or disagree, standard polling surveys. The idea is we use the survey to try to figure out how a population feels about a certain question. For example, do you like the color red? The idea of the survey is that we don't want to have to ask every single person in the population, so we'll ask a sample of the people in the population. If we asked a sample of the people in the population, do you like the color red, and then took the number of people who said yes and divided it by the total number of people we asked, that would be called our sample proportion. And we'll use the letter P to stand for the sample proportion. Now, one of the things that's going to affect the accuracy of your sample proportion is the number of people you've asked. The larger your sample size, the more accurate you would consider your sample proportion to be. So sample size is important. And we'll let N stand for the sample size. We still need something else. Imagine that you had a room of 100 people, and that 50 people in the room would have said yes to our question. 50 people like the color red, and the other 50 don't. Now suppose that we sample 50 people in the room. You might think that on average we should get about 25 people saying that they like red and 25 people saying that they don't like red. But we could get very unlucky and sample only people who like red. So our sample proportion would say that 100% like red. On the other hand, we could get very unlucky and find that we sample only people who do not like the color red. And there, our sample proportion would say 0% of the people in the room like red. So a survey needs something else, and what it needs is a confidence interval. And to find the confidence interval, we need to decide on a confidence level for our statistic. We'll let alpha stand for our confidence level. With P, N, and alpha, we can construct what's called a confidence interval. A confidence interval is a range of numbers, ranging from P minus Z sub alpha over 2. So Z sub alpha over 2 is a Z-score. Alpha, our confidence level, is a probability, so it's a number between 0 and 1. And N is our sample size. The confidence level alpha provides us with the confidence we have that the true proportion for our population is in between these ranges of values. Let's look at an example which will help us understand exactly what this means. Let's suppose we conducted a survey and there were 800 people in the survey. 556 said yes and 224 said no to the survey. Our sample proportion P is equal to 556 divided by 800, which is equal to 0.695. So roughly 70% of the people said yes to our survey. Recall, though, that the 800 people are only a sample of the true population. So what we're going to try to do is build a confidence interval. Now, in the confidence interval formula, the portion that we add and subtract to the sample proportion is oftentimes called the margin of error of our study. So we need to compute the margin of error for this study. But again, notice that this formula requires alpha, a confidence level. So first we have to ask ourselves, we're going to give a margin of error for this sample proportion. How confident do we want to be about the margin of error? And really, that's up to you. A standard confidence level is 90% or higher. So let's go ahead and choose a confidence level of 95%. So we're 95% sure that the statistic we're about to generate is valid. So first, let's find the margin of error. The margin of error for this study can be found by finding z sub 0.95 divided by 2 and dividing that by 2 times the square root of 800. Z sub 0.95 divided by 2, well, 0.95 divided by 2 is 0.475, so that's the z number we need to find. It's still divided by 2 times the square root of 800. We know how to find that z-score using the techniques previously discussed in this video. So if you look for this z-score, you'll find that it's approximately 1.96. And if you work this out on your calculator, you'll see that it's approximately 0.035. So the confidence interval for this study would give me a range of values of our sample proportion minus our margin of error, comma, our sample proportion plus our margin of error. For a confidence interval of 0.660 up to 0.730. So we're approximately 95% sure that somewhere between 66 and 73% of the entire population would have said yes to the question asked in our study. Another common way to represent this information would have been to take our sample proportion, 69.5%, plus or minus our margin of error, 3.5%. Now, what if we wanted to be more confident about our study? Do you think that's going to make our confidence interval wider or narrower? Another way to ask that is, do you think it's going to make a larger margin of error or a smaller margin of error if we want to be more confident about our statistic? Why don't you try alpha equals 0.98 for the same study and see if you can find the margin of error if you use alpha equals 0.98. So pause the video, work out the margin of error for alpha equals 0.98, and then see if you've got the same answer as I have. I found the margin of error to be approximately equal to 0.041, which would give me a confidence interval of 0.654 up to 0.736. Notice this is a wider interval. We were 95% sure that the correct answer was between 66 and 73%. But if we want to be 98% sure, we have to widen our range and say that we're 98% sure that the correct answer is somewhere between 65.4% and 73.6%. Suppose for this study I told you that I had a margin of error of only 0.0203, which is 2.03%. So again, recall when we wanted to be 95% sure, our margin of error was 3.5%. When we wanted to be 98% sure, our margin of error was 4.1%. So suppose I did a study, and again, we have 800 people in our study, and I came up with a margin of error of 2.03%. If I provide this statistic, how confident am I that it's correct, that my margin of error is only 2.03%? Well, recall that the margin of error, 0.0203, is equal to z sub alpha over 2 divided by 2 times the square root of n, where in this case I've surveyed 800 people. I need to figure out what alpha is to find my confidence level. To do that, first I need to solve for z sub alpha over 2. So my first step would be to multiply both sides of the equation by 2 times the square root of 800. And if you work this out, you'll see that z sub alpha over 2 is approximately 1.15. So let's look at a picture of what this is asking us. This is similar to a z-score, but notice that it's z sub alpha. So between 0 and this z sub alpha over 2, I want this area to be alpha over 2. My z number is 1.15. So first I should figure out what that area is. That area is the area found by looking at the probability that 0 is less than z is less than this z-score, which is 1.15. If you solve this problem using the techniques from the previous section, you should get that this is approximately 0.375. So this is the area between 0 and z sub alpha over 2. So alpha over 2 equals that area. Alpha over 2 equals 0.375. Solving for alpha by multiplying both sides by 2, we see that alpha is equal to 0.75. So this study, with a margin of error of 2.03 and a sample size of 800 people, we would only be 75% confident about that margin of error. Notice it doesn't matter what the sample proportion of the study is. A common practice when considering a survey is to decide on what margin of error you would like to have and how confident you would like to be, and then solving for the sample size, the number of people you would have to ask to generate the margin of error you want given the confidence level you want. An example of this can be found in your textbook, and it's a good idea to look at that example.